Hi, my name is Sofia Alvarez and I'm a Physics and Systems and Computing Engineering student at Universidad de los Andes, and today I am going to present the influence of depth cues on eye tracking depth measurement in augmented reality using the MagicLeap device, on behalf of Pierre Rambaud, Pablo Figueroa, and Jose Tiberio Hernandez. Alright, so our agenda for today would be introduction and related work, methodology, experiment, results and discussion of our work, and finally the conclusions of our paper. Alright, so regarding depth perception, we have that humans divide their environment in three subspaces, which are personal space for distances up to 2 meters, the action space for distances between 2 and 30 meters, and the distance space beyond 30 meters. We found that in mixed reality, in the action and distance spaces, there tends to be an underestimation of the distance at which an object is located. So, while in the personal space, there tends to be an overestimation of this distance. This will be later important for the focus of our paper. Also, we found that in the absence of visual aids, distance estimation tends to be of 0.9 plus minus 0.2 meters. In the literature, visual aids for depth perception are called depth cues, and they can be visual cues and oculomotor cues. Even though oculomotor cues such as vergence and accommodation do have a really positive impact on depth perception, we focused on the monocular cues, which can be brightness, shadows, texture, and focal depth, among others, but there are also binocular cues which can also have a really important effect on depth perception, and some of them are stereognosis and convergence. Alright, so also in the field of depth perception, we found that there have been studies about the influence of color, temperature, luminance, contrast, blur, and disparity, and also about the influence of shadows. And all of this have shown that depth cues can improve depth perception in VR and AR. In the eye tracking field, there have been studies about the relation between the accuracy of the measure and the distance. They found that the farther the objects are, the higher the relative error for the depth measure is. So in our investigation, we found that previous research has mainly focused on the human perception of depth, which is, of course, subjective as it is from the user's point of view. However, with the emergence of eye tracking technologies in mixed reality devices, vision focus can now be measured in terms of 3D spatial positions. So, what we want to know is if these depth cues that are really important to improve depth perception in mixed reality can also influence eye tracking measurement in the same way that they do depth perception. So this hypothesis arises from the fact that even though the measures come from a device, the computation done is based on the human physical reaction of each eye to the objects displayed in the environment. So to evaluate the influence of depth cues on eye tracking measurement, we compared the distance measured using eye tracking in the depth axis under varying conditions. So we chose two depth cues, lighting and texture gradient. And we chose these two because they are not only two of the most important depth cues in the literature, but also because they are reproducible on both virtual and real objects, which is ideal in an augmented reality environment. So, for watching or for noticing the facts, we could vary three factors, which were the environment lights, which could be diffuse, omnidirectional, or spotlights, the texture of the object, which could be polyester-like texture or smooth texture, and for control, we had the real object or the virtual object. Alright, so what we expected was that for lighting was that the light condition that had a major visual effect on shading would increase the precision of the depth measurement. And the texture condition with a major visual effect on shading would also increase the precision of such depth measurement. So for our experiment, we had 20 participants with an average age of 21.1 years plus minus 3.6. 13 of them were male and 6 of them were female. Their task was to sit in a chair, stare at an object during 30 seconds at 1 meter of distance, which is under foveal vision. So in here you can see the views of a schematic representation of our experiment. So here is a top view, and in here we have a right view. So from the top view, you can see that the user was located 1.5 meters away from the sphere in the depth axis, which is the z-axis, and it was located in 1.25 in x. This is in global coordinates of the object. And also, we can see that in such a way, the sphere is located in the origin in z, and 0 in z. And also in here, you can see that the user is located 1.5 meters away and that the sphere is located at 1 meter in height, so that it is mostly at the same height than the user. Alright, so we had 6 scenarios for each participant, and they were X, nature, texture, light, so X is for the number of the scenario. Nature could be real or AR or virtual object. Texture would be a smooth or polystyrene-like, and light would be diffuse or spot. So, for instance, this second sphere, which is 2 AR smooth diffuse, shows the second experiment with a virtual object whose texture is smooth and under diffuse light conditions. This one is 3 AR polydiffuse. The third experiment, AR or virtual object, polystyrene light texture under diffuse light conditions. Alright, so as you can see in here, we have the results for one participant. In this graph on the left, we can see the depth measures grouped by similar conditions of texture and under light varying condition. In blue, we have the diffuse light, and spotlight is in orange. So in here, it is easy to see that the depth measures in the spotlight scenarios in orange, in all of them, are more precise and accurate than in the ones with diffuse light conditions in blue. So the object is here represented with a purple cross, and as you can see, all the orange measures are closer than the blue measures. So it is also we can also note that mostly all of the measures are 10 centimeters away from 10 centimeters farther from the object, and this agrees with the literature, as users tend to overestimate distance in the personal space. Alright, so regarding texture, the polystyrene one has a positive effect when combined with the spotlights, and here you can see that scenario 6 has the most precise measures. Alright, so regarding texture, it seems that rougher textures which generate more shading, like the polystyrene-like texture, tend to give more precise results. As you can see, the red data are closer to the targeted object than the green data. So, however, in here, under the diffuse light condition, we can see that there is nothing that we can conclude. So in here, we have like we had the insight that texture was as a depth cue was only relevant if it was combined with another depth cue, such as a spotlight condition. So indeed, in these two experiments, in which we had a virtual polystyrene-like sphere, and in here under spotlight condition, and in here spotlights under polystyrene texture, had the best results in orange and in red, respectively. Alright, so considering all the participants, it is easy to see that scenarios 1 and 4 tend to have more dispersed measures, as they have the largest interquartile range and standard deviation. The spotlight scenarios tend to provide better results, and this is confirmed for all users. If we compare graph 1 to 4, 2 to 5, and 3 to 6, you can see that the interquartile range diminishes, which can also be seen, but less significantly, for the texture if we compare scenarios 2 and 3 and 5 and 6. So this is another insight for the fact that light is probably a more important depth cue than texture. Finally, we conducted a statistical analysis and we used ANOVA. So to run an ANOVA, we noted that the data distributed normally. We also had that there was homogeneity of the variance between the scenarios. We performed a Levin's test, and also we noticed that all the observed factors, light, texture, and the nature of the object, were independent, and this is true because they are all physical things of the scene that can be manipulated independently. In this way, we could run an ANOVA. However, as each subject participated to the 6 scenarios repeatedly, we have to run a repeated measures ANOVA. We ran a two-way repeated measures ANOVA to study independently the effect of the nadir in light and also the effect of light and texture. In the first ANOVA of nadir in light, we saw that nadir had no significant effect on measures, as the p-value is much greater than the alpha value. However, for the second ANOVA, we had insights that were similar to the ones we showed graphically before. So texture had no significant effect on measures with a p-value of 0.605, which is much greater than the alpha value of 0.05. And this is important because texture really had no significant effect if it was not combined with another depth Q. Lighting had a significant effect of measures because the p-value had a smaller value than the alpha value, and this is important because in all our scenarios we saw that lighting was more important than texture, and that lighting itself is a really important depth Q. We also noticed, however, that light plus texture had no significant effect as the p-value was again greater than the alpha value. This makes sense, as light and texture has only an effect if that texture has only an effect on depth measurement, if and only if it is combined with another depth cue, such as a spotlight condition, in our analysis. Alright, so to conclude, depth cues which improve depth perception can also improve the precision of depth measurement with eye tracking. However, not all depth cues have the same influence. For example, lighting was significant in our experiment, but texture was not. So texture was only significant when it was combined with depth cue of lighting, and so that texture may be used in auxiliary depth cue. We also noticed that depth cues also allow to reduce a standard deviation between subjects, and this may be important to develop apps that use, or to develop in augmented reality applications that use depth measurement so that they can standardize their value and improve user experience. Alright, so other studies that could be conducted for future work may be about the influence of shadows which are inconsistent with the objects and lights. It would be also interesting to note other distances different than 1 meter. It would also be interesting to include other depth cues in our analysis, maybe some oculometer cues or binocular cues or even other monocular cues. And also, it would be highly interesting to know the influence of the real lighting on the pupil size and eye tracking measure. Thank you so much for your attention, and I'm willing to answer any questions you have.